Unbelievable discoveries have emerged from the James Webb Space Telescope, JWST, the $1 billion time machine that just completed its first year of observations. Designed to capture the faint infrared glow of the universe's earliest luminous objects, Webb's vision has ventured back into the first few 100 million years after the Big Bang, allowing it to gather more and better data on infant galaxies than any other facility yet built. Yet, its haul of cosmic baby pictures has proven more abundant than most experts dared to dream. Candidate galaxies in the early universe are appearing in numbers that defy predictions, with dozens observed so far. This discovery has left scientists in awe. As Charlotte Mason, an astrophysicist at the University of Copenhagen, said, "We weren't expecting this." In the weeks and months following JWST's discoveries of surprisingly mature early galaxies, theorists and observers scrambled to make sense of them. Could the pack of atypically large and bright early galaxies be a fluke, perhaps due to errors in the analysis of the telescope's initial observations? If authentic, could they somehow be explained by standard cosmological models? Or perhaps they were the first hints that the universe is stranger and more complex than even our boldest speculations had ever assumed. Was the Big Bang theory wrong? Join us today as we delve deeply into how the James Webb Space Telescope broke the universe. To comprehend the issue, we must go back to when the universe was believed to have formed after the Big Bang. The newborn universe began cooling within a few million years, and the roiling plasma that filled space settled down. Electrons, protons, and neutrons combined into atoms, primarily neutral hydrogen. Things were quiet and dark for a period of uncertain duration, known as the cosmic dark ages. Then something happened. Most of the material that flew apart after the Big Bang is made of something we can't see called dark matter. It exerted a strong influence over the universe, especially in the beginning. In the standard picture, cold dark matter, a term that refers to invisible or slow-moving particles, was flung about the universe indiscriminately. In certain areas, its distribution was denser, and in these regions it began collapsing into clusters. Visible matter, meaning atoms, clustered around the lumps of dark matter. As the particles cooled, they eventually combined, and the first stars were born. These new sources of radiation reionized the neutral hydrogen that filled the universe during the so-called Age of Reionization. Through gravity, larger and more complex structures evolved, forming a vast cosmic web of galaxies. Meanwhile, everything kept flying apart. The universe is expanding rapidly. The cosmologist Edwin Hubble figured out during the 1920s that the universe is growing, and in the late 1990s, his namesake, the Hubble Space Telescope, found evidence that the expansion is accelerating. Consider the universe like a loaf of raisin bread. It starts as a mixture of flour, water, yeast, and raisins. When you combine these ingredients, the yeast begins fermenting, and the loaf starts to rise. The raisins inside it stand in for galaxies, expanding further apart as the loaf grows. The Hubble telescope observed that the loaf is rising much faster. The raisins are flying apart at a rate that defies their gravitational attraction. This acceleration seems to be driven by the repulsive energy of space itself, known as dark energy, represented by the Greek letter lambda. Plug values for cold dark matter, ordinary matter, and radiation into the equations of Albert Einstein's general theory of relativity, and you get a model of how the universe evolves. This lambda cold dark matter, lambda CDM model matches nearly all observations of the universe. One way to test this picture is by observing the very distant galaxies, equivalent to looking back in time to the first few 100 million years after the Big Bang. The universe was simpler then, making its evolution easier to compare against predictions. Astronomers first attempted to observe the earliest structures of the universe using the Hubble telescope. In 1995, over 10 days, Hubble captured 342 exposures of a seemingly empty patch of space in the Big Dipper. Astronomers were amazed by the abundance hidden in the inky darkness. Hubble could see thousands of galaxies at various distances and stages of development, extending back to much earlier times than anyone anticipated. Hubble would go on to discover some very distant galaxies. In 2016, astronomers found its most distant one, called GNZ11, a faint smear they dated to around 400 million years after the Big Bang. This was surprisingly early for a universe, but it didn't cast doubt on the lambda CDM model, partly because the galaxy is tiny with just 1% of the Milky Way's mass, and partly because it stood alone. Astronomers needed a more powerful telescope to determine whether GNZ11 was an anomaly or part of a larger population of astonishing early galaxies, which could help determine whether we are missing a crucial piece of the lambda CDM puzzle. That's why the James Webb Space Telescope, JWST, was conceived. Renowned as the largest, most powerful observatory ever launched from Earth, the JWST was built to revolutionize our understanding of the universe. Positioned 1.5 million kilometers away from Earth's interference and chilled close to absolute zero by its tennis court-sized sunshield, the ambulance based on its siren. The siren sounds higher in pitch as it approaches and then lower as it moves away. The farther a galaxy is, the faster it moves away from us as its light stretches to longer wavelengths and appears redder. The magnitude of this redshift is expressed as z, where a given value of z indicates how long an object's light has traveled to reach us. One of the first papers on JWST data came from MIT astronomer Rohan Naidu and his colleagues, whose search algorithm flagged a galaxy that appeared mysteriously bright and incomprehensibly distant. Naidu named it Glass Z13, indicating its apparent distance at a redshift of 13, farther away than anything seen before. The galaxy's redshift was later revised down to 12.4, and it was renamed Glass Z12. Other astronomers working on different sets of JWST observations reported redshift values from 11 to 20, including one galaxy called CERS 1749 or CR2Z71, whose light appears to have been emitted 13.7 billion years ago, just 220 million years after the Big Bang, barely a blink after the beginning of cosmic time itself. These potential identifications suggested that the neat story known as lambda CDM might be missing something. Galaxies appeared massive almost immediately in the early universe. "You don't expect to see massive galaxies," said Chris Lovell, an astrophysicist at the University of Portsmouth in England. Indeed, in a study published in November, researchers analyzed simulations of galaxies governed by the lambda CDM model and found that JWST's early bright galaxies were an order of magnitude more massive than those that formed at the same time in the simulations. Some astronomers and media outlets claimed that JWST was breaking cosmology, but not everyone was convinced. One issue is that lambda CDM predictions aren't always clear-cut. While dark matter and dark energy are straightforward, visible matter has complex interactions and behaviors, and no one knows exactly what happened in the early years after the Big Bang. Those chaotic early times must be approximated in computer simulations. The other problem is that it's hard to know exactly how far away galaxies really are. In the months since the first papers, the ages of some of the purported high redshift galaxies have been reevaluated. Some were downgraded to later stages of cosmic evolution due to updated telescope alignments. For example, CERS 1749 is located in a region of the sky containing a cluster of galaxies whose light was emitted 12.4 billion years ago. Naidu says it's possible the galaxy is part of this cluster, a closer interloper that might be filled with dust, making it appear more redshifted than it actually is. According to Naidu, CERS 1749 is intriguing regardless of how far away it is. It could be a new type of galaxy that we didn't know about, a very low-mass, small galaxy that somehow accumulated a lot of dust, which is something we don't typically expect for very distant galaxies. Everyone knew that the most definitive distance measurements would require JWST's most powerful capability. JWST not only observes starlight through photometry, measuring brightness, but also through spectroscopy, measuring light's wavelengths. If a photometric observation is like a picture of a galaxy in different colors, a spectrographic observation is like shining light through a prism to separate it into its components. The result is a spectral fingerprint of the galaxy's atoms and molecules, revealing its redshift and age. In July 2023, JWST delivered the first of these observations, causing jaws to drop. From December 2022 through February 2023, the telescope aimed at one region in the southern constellation Fornax for more than 200 hours, detecting over 400 previously unseen galaxies with redshifts above 8 and spectroscopically confirming 45 of them as being so distant. Most of the confirmed galaxies had already been identified through photometry, But this method revealed that one of the brightest of the early JWST galaxies had been hiding a secret. Although its redshift had been estimated as 14.3, making it the farthest galaxy ever observed, its spectroscopic redshift was actually a much more moderate 4.9, equivalent to 1.2 billion years after the Big Bang. Such redshift reassessments demonstrate why photometric and spectroscopic approaches must be complementary. According to Tommaso True, a UCLA astronomer involved in JWST's early galaxy work, spectroscopy requires a lot of telescope time, so astronomers are using the photometric redshifts to sort galaxies into distance bins and then confirming as many as possible with spectroscopy. Redshift is just the first step. As JWST refines its census of early galaxies, researchers will examine more subtle characteristics, such as the types of stars within them, whether they are pristine with only hydrogen and helium, or have already undergone nuclear fusion to create heavier elements. These findings will allow us to investigate whether these galaxies have enormous black holes at their centers, drawing matter into their gravity wells and powering them to great brightness. The early results from JWST show that whatever these galaxies are, they aren't what astronomers expected. JWST could show us that the thing we thought happened doesn't happen at all, said Mason, the Copenhagen astrophysicist. That would imply a more dramatic reimagining of the early universe, with dark matter somehow clumping differently or a faster rate of star formation than we ever thought possible. According to Lovell, there is no single answer. We may have to explore several modifications to the standard lambda CDM model, some of which might be correct and some of which might not be. In this case, he adds, we'll have to revisit our knowledge about the Big Bang to figure out where we went wrong. In just a year, the James Webb Space Telescope has transformed our understanding of the universe. Its powerful instruments have pushed the boundaries of human knowledge, revealing galaxies that have forced us to question the very foundations of cosmology.